Hello everyone, I hope you are doing well. In this video, we'll be continuing our solution for problem 21 from chapter 5 of Introduction to Statistical Mechanics by Roger Bowley. So this is the continuation of a problem, which means that half of the problem has already been solved in part 1 of this video. I'll share the link to the part 1 of the video where we have proved these three relations. Okay, and since the video has become really long, that is why I'm doing it in a separate part where we'll be calculating the average internal energy of a harmonic oscillator and average energy as well as standard deviation in energy for a two-level system with energies E and negative E. Okay, they have shown us this formula and we have to prove that the average internal energy of a harmonic oscillator equals this term. Okay, so let's quickly get started. Here we have average internal energy of a harmonic oscillator that we have to prove that it is equals to h cut omega by 2 plus h cut omega by e to the power h cut omega by kbT minus 1. Okay, this is something that we have to prove. And let's start with the general formula for the average internal energy that we have seen multiple times. And it's also mentioned in the problem statement that we know that average internal energy, the formula for average internal energy is given by, this is the formula, summation pi ei over I. And let's say in harmonic oscillator we know that the energies are given in n quantum number. Okay, so we'll replace I with n, because in harmonic oscillator we name those states with n numbers. We differentiate different states with n number. That is why we'll be using this formula. Okay, easy is that because I is showing that which state you are referring, and n also shows that, and that's the most conventional way of representing the states of a harmonic oscillator. That's why I'm using it. It's totally up to you if you want to use I here or whatever you want to use it. Okay, so this is the formula that we'll be using. Okay, we know that energy En of a harmonic oscillator is given by what are the energy states of a harmonic oscillator? It is given by En equals n plus 1 by 2 h cut omega. And what is n? N is 0, 1, 2, 3 up to so on infinity. Okay. And what else we can do here is that we can multiply h cut omega inside it, so that it's n h cut omega plus h cut omega by 2. I did it because you can see here. Okay, so that separation is good. Let us call it as equation number 2. Now let's put the value of Pn here from 1. We know that probability is equals to e to the power minus En by kBT divided by z. This is the formula for probability, and we just inserted it here. Then we have multiplied by En. Okay, we can take z outside of the summation sign, the reason being that z doesn't contain n. E to the power minus En by kt into En. Now we have the formula for the internal energy, and what else we have to do is to simplify it to this form. Okay, that's all which is needed because we have the formula. And what I want to do here is to insert the value of En right there and there as well, and to simplify some form and get some good form out of it. So let's do that. U bar equals 1 over z summation over n e to the power minus h cut omega plus n h cut omega plus h cut omega by 2 whole divided by kBT, okay, into En, which is n h cut omega plus h cut omega by 2. All right, that we just simply inserted the value of En here. Okay, so we can see here that we have this kBT divided by this whole term, so we can separate kBT on both of these values. It's just like we are multiplying it inside of this bracket, so we'll write h cut omega by 2 kBT. There will be negative sign here because this negative sign multiplies with this value as well as with this value, so there are two negative here, and n h cut omega plus h cut omega by 2 1 over z. Now we have two terms in the exponent of this base e. So what we can do is to separate both of these terms with a common base, so that we have e and h cut omega by kBT multiplied by e with this power over it. These are the rules of exponents, that if we have two terms over there being added with each other, so we can separate them into two terms with the common base, which means that both of these terms will have same base, which is e. Okay, so that's how we did it, and h cut omega plus h cut omega by 2 remains the same. Now we can see that this term doesn't contain n in here, so we can take it outside of this summation sign. E to the power minus h cut omega by 2 kBT divided by z summation. We have this term left inside, and h cut omega plus h cut omega by 2. Next is that we can multiply this term here and with this term as well, so that we may get a simplified form. So there is this whole bracket summation n e to the power minus n h cut omega by kBT multiplied by n h cut omega plus h cut omega by 2 summation n e to the power minus n h cut omega by kBT. Okay, I wrote it here outside of this summation because it doesn't contain n, and this summation was multiplied by both of these quantities. That is why it will appear with both of these quantities, and we can simplify it further. H cut omega could be taken outside of the summation n e to the power minus n h cut omega by kBT. Okay, plus h cut omega by 2 summation over n e to the power minus n h cut omega by kBT. Let us call it as equation number 4. Yes, there is one more thing that we can do here. Here is z, which is the partition function. Z is equals to, we know that z is equals to e to the power minus en by kBT summation over n. Okay, this is the partition function, and if we insert the value of en here, so we got en is h cut omega by 2 plus n h cut omega. I just wrote them like that. It's the same thing. So we will separate the bases with different powers, so we get the same thing as we got previously. We can take this term outside, so it's e to the power minus h cut omega by 2 kBT into summation and e to the power minus n h cut omega by kBT. Okay, and we can insert this value of partition function right here, and we'll have some cancellations, and we'll get some simplified form as a result. Okay, so let's do that. Let's put this partition function's value right back into this equation. And here I hope you are not confused. I just wrote h cut omega by 2 first and h cut omega later. That doesn't bring any difference. So let's put z here. So putting in 4 so that we may get some simplified form, and we may need only few simplifications later. Z u bar equals e to the power minus h cut omega by 2 kBT divided by z. So z is e to the power minus h cut omega by 2 kBT into summation e to the power minus n h cut omega by kBT. That is z. Then we have bracket, and we have inside h cut omega summation and e to the power minus n h cut omega by kBT with n here as well, one more n, plus h cut omega by 2 summation n e to the power minus n h cut omega by kBT. This cancels out. U bar equals, now this is in the denominator, outside, it's outside of these brackets, but it's in the denominator, so it means that it will be multiplied with this and this value as well. So we can write this in the denominator of this value and this value as well, because you can see that z was outside of this whole bracket, which means that z is common to both of these quantities, so it will appear in the denominator of both of these quantities. So that's what we are gonna do here. H cut omega summation n e to the power minus n h cut omega by kBT divided by n e to the power minus n h cut omega by kBT plus h cut omega by 2 summation n e to the power minus n h cut omega by kBT and summation n e to the power minus n h cut omega by kBT. Since they are exactly the same, so they will be cancelled out, and we'll be left with h cut omega by 2 here, which I'm writing here. And here we have h cut omega into summation and n e to the power minus n h cut omega by kBT divided by n e to the power minus n h cut omega by kBT. Really simplified form. Now we need to calculate these two summations. We'll plug those values right back into this equation and we will get our form. Okay, so let's calculate these two summations now. We are almost done. Okay, this problem is almost done. We just need to evaluate these two summations, and first of all I'm gonna evaluate this summation in the denominator because because it's really easy. And we have, let's calculate these summations, because there are few summations, integrals and other things which are really frequently appearing in various formulas and derivations. These summations are one of them. Okay, you'll see them in Planck's derivation for black body radiation, and in many other formulas you will see them in Maxwell distribution function and many others. Okay, so that's a really important summation and you should know how to evaluate it. So we are gonna do this. Here we have the summation in the denominator, and interestingly from this summation we'll evaluate the value of this summation. That's why I'm calculating this one first. Okay, and knowing its value we can find out the value of the one in the numerator. So this is the summation, and here we have, if we expand this summation into series, then we just need to put the value of n starting from 0 to infinity. So first of all we'll put the value of n to be equal to 0, so it's e to the power 0. It's my job to explain every step and everything. If you just wanna skip to the part where I have calculated their value, you can do that. But the most sensible and responsible way of doing problems is to understand each and every step. Okay, so we'll put the value of n to be equal to 0, so it will make the whole term 0 in the power, so it's e to the power 0 plus e to the power negative. In place of n we'll put 1 now. N value is 0, 1, 2, 3, 4, 5 up to so on. So negative as it is, in place of n you'll write 1 into h ket omega by kBT. It's simply h ket omega by kBT. Then you will put n equals to 2, so it's e to the power minus 2 h ket omega by kBT, and e to the power minus 3 h ket omega by kBT plus up to so on. Okay, so let me tell you people that, okay, in place of e to the power 0 we can write 1. We have plus e to the power minus h ket omega by kBT plus e to the power minus 2h ket omega by kBT plus e to the power minus 3h ket omega by kBT up to so on. Now this series, this summation forms a geometric series. Okay, geometric series geometric series is the one in which the ratio between two consecutive terms in the series remains the same. It means if you divide the second term with the first term, the value you will get will be equals to the value you will get by dividing the third term by the second term. Okay, whenever you will divide two consecutive terms in that series, the ratio will remain the same throughout. Okay, wherever, doesn't matter at which point of the series you are finding out the ratio of two consecutive terms, the ratio will remain the same. You can test it out, and summation of geometric series is given by this series forms a geometric series with ratio. You have to calculate the ratio. Okay, so ratio would be equals to dividing any two consecutive terms. So I'm taking the second term and first term. I'll divide the second term by first term, and whenever you are finding out the ratio, what you have to do is to divide, is to take the next term as the numerator and the previous term as the in the denominator. Okay, you cannot reverse the order. For example, you cannot do it like a1 divided by a2. No, you have to do a2 divided by a1 to find out that ratio, because that is how we have formulated the formula for its summation. Okay, so you can see here r would be equals to simply e to the power minus h ket omega by kBT. So this is the ratio, and you would have even calculated it by dividing the third term by second term. You'll get the same result because it's a geometric series. Okay, that's the property of geometric series. The ratio will remain the same between two consecutive terms, which means it's not like if you divide this term with this term, okay, and this term with this term, you'll get similar result. No, that's not the meaning of geometric series. It's always true for the consecutive terms. So that is the ratio, and sum of geometric series is given by the general formula for the summation is sum is equals to, sum means this thing that we have here, e to the power minus n h ket omega by kBT. That would be equals to first term of the series divided by 1 minus r. First term of the series, that we can see it's 1 here. This is the first term, second term, third term, fourth term, and so on. This is the first term. So we'll write first term in the numerator divided by 1 minus r. R is the ratio. So let us insert these values here and see what the sum is. Sum equals, first term was 1, that is so good. 1 minus r was e to the power minus l e to the power minus h square omega by kbT. This is the first sum that we have here. Alright, now let's calculate. Let me call it as 6. Okay, now let's calculate the second sum, and for that purpose what I am gonna do is recall this. Okay, I'm rewriting it. Okay, this same series I'm rewriting here. Its expansion. We had summation n e to the power minus n h square omega by kBT, that is equals to 1 plus e to the power minus h square omega by kBT plus e to the power minus 2 h square omega by kBT. If you see, the series in the numerator is not a geometric series, okay, in a direct way. It doesn't forms the geometric series, so we have to use some indirect methods to evaluate its summation. Okay, this is the expansion, and we can replace this thing with this because it's equal to this. So we can write 1 over 1 minus e to the power minus h square omega by kBT to be equals to 1 plus e to the power minus h square omega by kBT plus e to the power minus 2h square omega by kBT plus e to the power minus 3h square omega by kBT up to so on. We can write it right because this summation is equals to this, so we can write it like that. All right, now next what I'm gonna do is to let, for convenience, I'm gonna let h square omega by kBT to be equals to x. Let h square omega by kBT is equals to x, so the summation will look like simple 1 plus e to the power minus x plus e to the power minus 2x plus e to the power minus 3x plus up to so on. This is a really simple form. Now we'll differentiate both of these sides with respect to x. Differentiating both sides with respect to x. So d by dx, we can write this term as 1 minus e to the power minus x whole power minus 1. It's in the denominator, so we can write it like that so that the differentiation becomes easy, and we'll apply differentiation here as well. Okay, so next we'll use the power rule here. So the power minus 1 will come here. 1 minus e to the power minus x, power will be reduced by 1 dot derivative of inner term 1 minus e to the power minus x, that is equals to, we'll take derivative of each of these terms. So derivative of 1, since it's a constant, is 0, plus derivative of e to the power minus x is e to the power minus x into derivative of its power. Power is minus x, derivative of minus x is minus 1, so it's simply minus 1, plus we are almost done. Okay, don't be afraid, it's just a simple method. When you will practice it enough times, it will become really easy for you to do it repetitively you can do it easily. So derivative of e to the power minus 2x is e to the power minus 2x as it is, derivative of its power, which will be minus 2. Power is minus 2x, if you take its derivative, it's actually minus 2 then. And similarly, derivative of e to the power minus 3x is e to the power minus 3x into minus 3 plus up to so on. Okay, so we can write minus 1 minus e to the power minus x whole power minus 2, and we have d by dx of 1 minus e to the power minus x. So the derivative will be applied inside. Derivative of 1 is 0 minus derivative of e to the power minus x is this. Derivative of 1 is 0 minus e to the power minus x, derivative of its power minus 1. Okay, I hope you got it. And that is equals to, we have here minus e to the power minus x minus 2 e to the power minus 2x minus 3 e to the power minus 3x minus up to so on, like that. As you can see, after taking the derivative, these terms become negative and all of the positive signs will become negative. So the series has changed. Now what we can do is to take negative as common, because it could be taken as common. So minus 1 and this minus will cancel out and e to the power minus x is left, equals this negative sign will be taken common. So we have the positive series now. Again, 2 plus 3 e to the power minus 3x plus 4 e to the power minus 4x plus up to so on. These two cancels out and we have e to the power minus x divided by 1 minus e to the power minus x. It's negative power here, sorry, positive power. Okay, it will become positive power in the denominator, and that is equals to e to the power minus x plus 2 e to the power minus 2x plus 3 e to the power minus 3x plus 4 e to the power minus 4x plus up to so on. Now let's put the value of x right here, that is h cut omega by kBT. Putting, if you do that, e to the power minus h cut omega by kBT divided by 1 minus e to the power minus h cut omega by kBT whole square, that is equals to e to the power minus h cut omega by kBT plus 2 e to the power minus 2h cut omega by kBT plus 3 e to the power minus 3h cut omega by kBT plus up to so on. And if you notice that this series on the right hand side is actually the series that we had in the numerator. This is equals to summation n e to the power minus n into e to the power minus n h cut omega by kBT. If you put n equal to 0 in this summation, here n will be 0, it will be multiplied with this exponential sign to make the whole term 0, and there is no term corresponding to n equals to 0. That's the reason. If you put n equals to 1 e to the power minus h cut omega by k2, that's the first term. If you put 2 here instead of n here, you write 2, it's 2 e to the power minus 2h cut omega by kBT. N equals 3 and 3 here as well, 4 and 4 here as well, and so on. So that series on the right hand side is actually this series, and this is its summation. Okay, so I did the whole thing just to make you people sure that how you know we got this result, and you should know it because you can't remember every result every time. You should know how to derive them. All right, so now let's put these values. Let's say we call it 7. This is 7, this is the sum in the numerator, and 6 is the sum in the denominator. Let's put these values right back into the equation number 5 to get our final result, which is almost now accomplished, because we just need to cancel something and it's all done. U bar equals h cut omega by 2 plus h cut omega. In numerator we'll write this term, it's e to the power minus h cut omega by kBT divided by 1 minus e to the power minus h cut omega by kBT whole square, and divided by, I'm using division sign, we have this term and we write its summation. It's 1 minus e to the power minus h cut omega by kBT. Okay, 1 divided by this, And when we'll change this thing, division to multiplication, what happens is it will become inverse. E to the power minus h cut omega by kBt divided by 1 minus e to the power minus h cut omega by kBt whole squared. Multiply sign will become numerator now. When division changes into multiplication, this happens. And whenever you have multiple terms and they are being divided, so it's always a safe option to do this thing that we used to do in high school. So this and this, one of them cancels out, so it's only one term in the denominator. Let's simplify it further to get the form that we need. It's e to the power minus h cut omega by kBt divided by 1 minus e to the power minus h cut omega by kBt. And if you notice, what we need to get, what form we need to get is like that. It's positive power in the denominator while we have a negative power here, so that could be achieved really easily. And for that purpose, what we'll do is, this is negative power in the numerator, we'll take it in the denominator. It will be multiplied by both of these terms, and when we'll simplify, we'll get the result, the form of result that we need. So we'll multiply it. Multiplying with 1 gives the same term. Multiplying with this, h cut omega by kBt. Now you can see both of them have same basis. It's e and it's e, and powers will be added. So it's positive power, negative sign, h cut omega by kBt. H cut omega by kBt minus h cut omega by kBt. It's e to the power 0 left. kBt minus e to the power 0. E to the power 0 is 1. So here we are. Finally, we proved that the average internal energy of a harmonic oscillator is equals to this term. Okay, that is how we have proved it. And I think we have to evaluate the average energy of a two-level system as well as its standard deviation in next video, because that was a bit lengthy. Hence, I'll meet you in next video, the part 3, where we'll evaluate the fifth relation. If you have any queries, you can ask me in comment section. Like, share, and subscribe. Goodbye.